Okay, so now we're going to talk a little bit about other volcanic landforms. Um, so the first one that we're going to cover are calderas. Calderas are depressions that are left by a collapsing crater. First, what happens is an eruptive event partially empties the shallow magma chamber underneath. Then the summit of the volcano collapses, causing the caldera itself. And then sometimes the caldera gets filled with water. And then even some other times after the caldera has been filled with water, there is a resurgent dome inside caused by volcanic activity underneath. Calderas can occur from three different types. The first type is a crater-like type caldera, which are caused by the collapse of the summit of a large composite volcano, which forms an explosive eruption of silica-rich pumice and ash fragments, and then after its eruption it collapses. A second type of caldera are a Hawaiian type caldera, which are caused by the collapse of the top of the shield volcano, caused by usually subterranean drainages from the central magma chamber, which has happened and is seen in, for example, Mauna Loa in Kilauea. And then the third type of caldera are the Yellowstone type caldera. A collapse, this usually is a collapse of a very large area caused by the discharge of huge volumes of silica-rich pumice and ash along the ring fractures. So we'll go through the three different types in the next slide. For the first type of caldera, Crater Lake is a perfect example. It is a remnant of the Mount Mazama eruption that happened about 7,000 years ago. The resurgent dome from volcanic activity underneath is what we know now as Wizard Island, and it is right here inside of the lake. Another example of this type of caldera is the Greek island of Santorini. Some of you may know it or know of it as a beautiful destination place to be. And it is obviously in the Aegean Sea, where most of those Greek islands are for destinations. The second type of caldera is typically in large shield volcanoes, and as I said, Mauna Loa and Kilauea both have these type of calderas within their summits, I should say, and they are about 4 kilometers in size. They have steep cliffs on the edges, which makes the inner part of the caldera look like a vast and flat bottom pit. The third type of calderas, thankfully, we have not had one occur in human historic times. Yellowstone last erupted about 640,000 years ago, and in the map you can see the extent of the ash from that eruption. The Lava Creek ash bed, which is this gray one right here, is that extent. But then you also see the other two eruptions ash extent. Although an eruption of Yellowstone would possibly have huge implications to us as a species, I doubt that it would fully eradicate us, but only time would tell if it were to happen during our lifespan as a species. Although an eruption in Yellowstone may occur due to the huge magma reservoir that still exists beneath Yellowstone, the constant seismic activity and also the hydrothermal features that are present within the caldera, as well as the eruption that is due to occur, if you see the trend of eruptions every 700,000 years apart or so, an eruption itself is not imminent right now necessarily. Yellowstone is probably the most studied and monitored volcano in the world, so I think that we will be able to at least have a little bit of a heads up before it goes off. I myself am one of the geologists that have done research in Yellowstone, checking for water chemistry in the hot springs and in the fumaroles within Yellowstone. Other examples of this third type of caldera are the Valles caldera in New Mexico, La Garita caldera in Colorado, and also Long Valley caldera in California. But Yellowstone is by far the greatest one that we know of right now. Another volcanic feature are basalt plateaus or fissure eruptions. These are eruptions that typically come from a fissure in the weak ground that is typically experiencing extension rather than from a cone eruption. The diagram on the top right shows how that work is done by the fissure, basically. The basalt from the picture associated with the diagram to the right, so this one right here, are of a basalt that is near Idaho Falls. These formed in pretty much that manner, and some of the basalts here in the most southwestern part of Idaho did as well. The Columbia River basalts near our home, a little bit to the west of us, are an example of this volcanic feature. In the map that's at the bottom right here, you can see the extent of the Columbia River basalts and also of some of the other basaltic rocks that occur in Idaho that are not associated with the Columbia River basalts, but by other features and other geologic events that occurred, and we'll talk about some of them later on. The picture on the right is me at Palouse Falls, which is in southeastern Washington. Those are the state falls. And you can see all of the basalt flows spreading miles and miles away by single sort of events, if you would, from the fissure eruptions, and as they flowed many, many miles in aerial extent, as you're seeing obviously from the map. We also have lava domes and volcanic necks for other volcanic landforms. You may also see these lava domes inside the craters of volcanoes, and they are characteristic of rhyolitic or even sometimes andesitic magma, so again felsic or intermediate in composition. They're usually a few tens of meters high, and they typically form following an eruption. They are typically the ones that produce consequent pyroclastic flows from the coming eruptions. Lastly, we also have the volcanic necks and dikes. We covered dikes a little bit, specifically in chapter 4, as they really are intrusive bodies. In fact, volcanic necks are intrusive bodies as well, because they did form, inside of the Earth's surface officially. But once the volcano sites have been eroded away, the crystallized magma that did in fact form inside of the conduit of that volcano is what remains standing, and that is what the volcanic necks basically are. Shiprock in New Mexico, which is about 500 meters high, is a great example of these volcanic necks. And again, many times you see the volcanic necks associated with dikes that are coming towards it or going away from it, depending on how you want to see it. And we'll see not the volcanic neck, but we'll see the dikes sort of leading to the volcanic neck during our field trip. Alright, so our last section here is going to be plate tectonics and volcanism. Geologists have known for decades that the distribution of the Earth's volcanoes is not random. Most are located along ocean basins, mostly within the circumference of the Pacific Ocean, which is a belt known as the Ring of Fire, not to be confused with the One Ring, which is Fortune Mount Doom. The Ring of Fire represents areas where denser oceanic lithosphere is subducting under the continental lithosphere. However, there are other innumerable seamounts from outside of the Ring of Fire in areas along mid-ocean ridges, like in Iceland, for example. And we also have seamounts and large volcanic basaltic igneous provinces in areas where we have mantle plumes rising. The first two types of volcano locations, the Ring of Fire volcanism and the mid-ocean ridge volcanism, align with lithospheric plate boundaries, but the third ones that I mentioned, meaning the seamounts or the volcanoes and large basaltic igneous provinces caused by the rising of those mantle plumes, will not align with the plate boundaries. So they kind of look like they're out of place in the map. Examples of these are the Hawaiian Islands, the Galapagos Islands. So let me point them out so that you don't get lost. The Hawaiian Islands, the Galapagos Islands, the Easter Island for the seamounts or volcanoes. And then we have large basaltic igneous provinces like the Columbia River basalts, which I had mentioned before. And in this case, they kind of do align, but when they were formed, they did not necessarily. But we also have, for example, the Deccan traps, which are over here, and we have the Parana basalts, which are right here, amongst many which can be found around the globe. For example, the Siberian traps as well in Russia up here. I encourage you to check image 5.32 of the book. Here you can see all of these different igneous basaltic provinces and hotspots that are associated with mantle plumes. So again, these types of features are named hotspots when the mantle plume itself leaves its mark on the Earth's surface. So once there is some sort of feature on the surface, we call it a hotspot. But it is the cause of a mantle plume that is rising towards it due to its lower density. Okay, I already covered the different plate boundaries in chapter 2, so I won't go in depth here, but I did want to point out that when you have oceanic or oceanic continental convergence of plate boundaries and subsequent volcanism, the typical features formed are a volcanic island arc, or simply an arc, or island arc, in the oceanic lithospheric convergence, and you have a continental volcanic arc in the oceanic continental convergence. Okay, so examples of those are the Cascades as the continental volcanic arc between the oceanic and continental convergence, and then examples of the volcanic island arc are the Aleutian Islands right here that are occurring due to the convergence of oceanic and oceanic lithospheric plates, or part material, I should say. Alright, this image here shows you some very good examples of the different types of volcanism around our globe, from seafloor spreading, rifting, oceanic convergence, oceanic continental convergence, and intraplate volcanism caused by hotspots. Also, intraplate volcanism caused by these gigantic basaltic plateaus, which are by hotspots basically, but not trackable, if you would, within the plates movements because they happen at a very fast speed all at once kind of thing. I suggest that you look at this figure with more detail. It is 530 of your book. And I encourage you to check the different locations that they point at right here and other locations from, for example, this image beforehand, so that you become more instructed in the future. All right, so with that, we finished chapter 5 and we move on to weathering and soils in chapter 6. So as always, if you have any questions, please email me, and I hope that this presentation was useful and informative.